Hello everyone, in this video we'll solve question number 3 on the topic of stresses and pore pressure in soils. So let us see what this problem says. So we have here a level site with the following soil profile. So we have 3 meters of gravel, and we have 2 meters of sand, and then we have 3 meters of clay, and everything is being underlain here by a rock layer. So the following construction sequence is then carried out. The uppermost 2 meters of gravel is excavated. So within this 3 meters of gravel, so we will have 2 meters to be removed entirely from the site. And then a very large diameter oil storage tank is built at the new surface. The depth of oil in the tank is 6 meters, and the specific gravity of the oil is 0.8. So after the excavation here of 2 meters of the gravel, so there will come a load from a very large area. This is the key word, from a very large area representing a tank. And we are given here the information about the content or the oil in this tank. The mass of steel in the tank is negligible compared to the mass of oil in the tank. This means that we will only consider the weight of the oil itself inside. Determine the change in vertical effective stress caused by construction at the bottom of the clay layer. So we have here, this is the bottom of the clay layer represented by point A, and we are required to calculate the change in effective stress at point A or anywhere here along this bottom of the clay layer due to the construction sequence that is made of 2 parts. Part 1, removal of 2 meters of the gravel, and part 2 is construction of a large diameter tank. So the essential knowledge that we need to have to tackle that problem: first, we need to understand again the meaning of pore water pressure, effective stress, and total stress in the soil. That's in general. And also we need to know the meaning of stress at a point or level due to a large loaded area, given here that we will have a tank of very large diameter. So solution strategy: we need to treat the excavation as a negative load. So we have these 2 meters of gravel, so we'll see how to handle that. And then we need to determine the effect of the tank load on point A, which, like I said, it represents the whole bottom of the clay layer. So let us take this step by step. Now this is the original soil profile, and then for the construction phase 1 or A, we will need to remove 2 meters of the clay. So this is why here you have this clear area of the gravel. We removed 2 meters of the gravel. So based on that, the stress after removing 2 meters of the gravel, that's phase 1 construction. Remember, because the problem is concerned with the change in stresses, you don't have to calculate all the stresses, total stress, pore water pressure, and effective stress from the difference between the total stress and the pore water pressure at point A. It may suffice in some problems just to work directly on the change that will happen due to certain loading condition. So here I have 2 meters of gravel excavated, so I can basically use this information directly to calculate the change in stresses at point A. So now point A got relieved of 2 meters of dry gravel due to excavation. This is due to excavation. So basically I can then substitute here in this equation and say, okay, I have change in the effective stress at point A equals the depth or the height of the soil removed times the unit weight that was here. I'm giving the unit weight here of the gravel above the groundwater table as 16. If we go back to the problem, so we have here 16. So we are using this basically to work out the change in stresses. That's 32 kPa decrease. So the result of phase 1 construction is a reduction in the effective stress at point A. But remember, very important for you to know that every other point here in the profile would be relieved of the same 32 kPa due to removal of these 2 meters. You need to know that. If we calculate the change in stresses at A, if we calculate it at point here in the middle or at the boundary here, eventually that the result should be just 2 times 16. Now let us see phase 2. Phase 2 construction, after I removed the 2 meter of clay, is to bring this load here from the tank load. Remember the key word of a very large diameter tank. So it means that we treat this as if we have here very, very large, covering the whole arbitrary area that I'm drawing here. But we really need to know what load this tank will bring, because we are not given this distributed pressure directly, but we are given a height of the oil inside the tank, and we are given the specific gravity of the tank. So the uniform load over a large area produces the same stress at any horizontal level and also at any elevation, i.e. as an overburden pressure. Very important. Like I said, from phase 1, when we removed these 2 meters, the stress relief was the same everywhere, horizontally and vertically. This also applies to the tank load, because the tank is covering a very large area. So whatever pressure this tank will create here, it will be exactly the same as being felt by point A or above or anywhere within this zone of the existing soil profile. It's going to be exactly the same. Reason being, it is actually applied over a very large area. Let us calculate the tank load now. The load in the tank is 6 meters of oil, and the oil is given specific gravity 0.8. The definition of a specific gravity, it is the ratio between gamma oil, the unit weight of the oil, and the unit weight of water, or exactly the same for density of oil by density of water. So based on this, I can work out the unit weight of the oil would be 0.8 times the unit weight of the water, which is 7.84. Yes, as you expected, the unit weight of the oil is lower than or is less than the unit weight of the water. So I have 7.84 kilonewton per meter cubed. Now I have 6 meters of oil height, and I have the unit weight of the oil. Simply multiply them to get the pressure that would be applied on the ground surface due to the tank load. So 6 meters height here times 7.84, we just calculated, it's 47.04 kPa. This means that the tank will produce a uniform load here. You can consider it because of the being large area, and this value is 47.04 kPa. By definition, I keep repeating myself that this 47.04 kPa will be felt everywhere within the soil profile. So the change in stress at point A due to the tank load will be 47.04 kPa, and this is increase. Now the question asks for the net change in the effective stress due to the combined effect of phase 1 and phase 2. So I can simply just add these two together at point A. So I have minus 32 kPa from phase 1, remember, because it was stress relief, at plus 47.04. So I have 15.04 kPa, that's increase. So point A, or the bottom of the clay layer, will feel increase in the pressure or in the effective stress specifically of 15.04. For this particular problem, given the condition, everywhere within the soil profile will exactly feel the same increase in effective stress of 15.04 kPa. So I'll see you in another video. Hello everyone, in this video we'll solve question number 5 on the topic of stresses and pore pressure in soils. So let us see how we can solve this problem. So we have here the total stresses shown in the figure are applied at a point in a soil mass. The pore pressure in the soil at the point is U. So this is the soil element. It represents a point. This is just a point. And we normally show the stresses at a point using a virtual small square of that nature. So determine what value you would need to take if the minor principal effective stress at the point was to be 0. Let us see again. I have a point, and at this point, this is a stress state given as total stress, the total stresses. Okay, and at this point also there is a pore water pressure. Its magnitude currently is U. Remember, U, pore water pressure, is basically equal in all directions, unlike the general case of the earth pressure. So this is what's required. What value of the pore pressure should we take so that the effective minor stresses is 0? The minor stress, we call it sigma 3. The major stress, we call it sigma 1. If we are talking effective, just we add the dash. So sigma dash 3 needs to be equal 0. But the problem given here is with total stress values. So the essential knowledge, you need to understand the meaning of pore water pressure, effective stresses, and total stresses in soil, which we covered in many problems already within this course. Also, we need to know Moore circle for interpretation of stress conditions and the formulas associated with Moore circle, as we will see later. Solution strategy. Basically, if the stress condition here is for total stress, so basically we need to determine first the major and minor total stresses. These are not the major and minor total stresses. This is just a stress state along a plane making 45 degrees with the horizontal and obviously the normal to it. So we need to use this information to work out the existing total major and the total minor stresses. Once we know the total major and minor stresses, we can subtract U from them to get the effective values. So apply the effective stress equation on sigma prime 3 or sigma dash 3. Why sigma dash 3? Because here we are interested in the minor stress only. And when we do that, we should be able to get the U required. Let us jump into it and see how we can solve this beautiful problem. Again, so this is a problem. I want you to understand the problem. So we have a point here. This is why I made this too small here. If you enlarge it, it becomes this, which is basically the problem we have in hand. So every single point here in the ground can have infinite directions of stresses. The existing ones, the one that we already have here, can be resolved into as many directions as you like. But only two of these directions will have only the major and minor principal stresses. Why I'm saying only here? Because by definition, the effective major and effective minor stresses, they don't have any shear stresses associated with them. Now, let us get into the task of finding the total principal stresses. You may be tempted to use this equation. Here, this is a very popular equation to get the major and minor stresses. But remember, this is what I put here and advising you not to fall into this trap. This is only applicable when sigma x and sigma y applies to vertical and horizontal planes. The problem we have in hand here, the given planes are inclined, so we cannot use this formula. Alternatively, we will be using this formula. Sigma theta equals half sigma 1 plus sigma 3 plus half sigma 1 minus sigma 3 cosine 2 theta. So what do we have here? What is sigma theta? Sigma theta is basically the stress applied to a plane that makes an angle theta with the horizontal. So our angle here is 45 degrees. Sigma 1 and sigma 3, we are chasing them. So this is equation 1. Sigma theta given, yes, sigma theta is given, as we will see in a second. And also tau theta, this would be the shear stresses applied to a plane that's making theta with the horizontal. So which we have it here, like I said, theta is 45 degrees. So given here, theta is 45 degrees, sigma theta is the normal stress on the plane that make an angle theta. So the plane that make an angle theta, this angle is 45, which is also this plane here, it's actually 50 because 50 is the normal stress. So this means that sigma theta is 50. Likewise, tau theta is the shear stress along the plane that make 45 degrees, given to us here as 30 degrees. Now we can substitute in 1 and 2 and solve. as follows. Now sigma theta is 45 degree. I'm just substituting in this equation 1, and I am trying to get sigma 1, sigma 3. So I substitute here. Theta is 45 degree, so 2 theta would be 90 degree. That's equation 1 dash. Likewise for the tau theta is 30, and I have half sigma 1 minus sigma 3 sine 90. Remember, what I am doing here is basically to determine the total measure and the total minor stresses from the total stress regime given at this particular point, because I will use the total minor stress to get the effective minor stress, which will give me U that we are trying to find. Now, when you apply sine 90 here is 1, and the cosine 90 here is 0. So when we process 2 from equation 2, sine 90 is 1. So you will put 1 here and rearrange. So this is giving me sigma 1 equals 60 plus sigma 3 when you work out this equation. I can go back now and substitute in 1 dash. So 45 equals 1 half 0.5 parentheses here, sigma 1 substitute 60 plus sigma 3, and you already have sigma 3, and this term here is cancelled because cosine 90 is 0. I can solve this problem now, simple, and this is giving me sigma 3 equals 15 kPa from this equation. Sigma 3 plus sigma 3, that's 2 sigma 3, and you rearrange, so 2 sigma 3 equals 90 minus 60, that's 15 kPa. Now I managed to calculate the total minor stress. By definition, the effective minor stress is the total minor stress minus U. For this particular problem, it's asking me what U should be so that sigma dash 3 equals 0. Simply substitute here. Sigma 3 prime equal, by definition, 15 minus U. 15 is what we have got from here, minus U, and this is giving me U equals 15 kPa. That's compression, obviously, because I am considering here the compression to be positive. So for this particular problem, at this point A, you need to subject this point A to a pore pressure of 15 such that this total stress regime will eventually make the effective minor stress equal 0. I'll see you in my next video. Hello everyone, in this video we will solve question number 6 on this series of stresses and pore pressure in soil. So let us jump into it. So I have an interesting problem here. An elastic soil is confined laterally and is actually compressed under drained conditions. In soil mechanics, the loading imposed on the soil is called K-naught compression for this particular case, or consolidation. Show that under the K-naught condition we have this correlation, that the effective stress in the horizontal direction X divided by the effective stress in the vertical direction Z equals the effective Poisson's ratio mu dash divided by 1 minus mu dash. So this is here Poisson's ratio for drained conditions, or we call it the effective Poisson's ratio. So essential knowledge here, we need to understand the definition of K-naught and the definition of Poisson ratio. I'll explain this in a second. And also we need to understand the meaning of lateral confinement. Here the keyword is confined laterally. Confined laterally means that the soil is prevented from experiencing lateral strain or lateral deformation. And we apply this to the concept of consolidation. As you know, you apply a vertical load, or perhaps you will study this next. You apply a vertical load while maintaining the boundaries of the soil in rigid conditions so that the soil is prevented from moving laterally. Solution strategy, we'll need to apply this concept of lateral confinement condition to the formula involving K-naught and the Poisson ratio. We will see this in a second. Very interesting problem. Now let us see here, when we have a general soil element in the three-dimensional sense, this soil element will experience vertical effective stress sigma dash Z everything is effective here. The minute you mention K naught, it applies only to effective stresses. So this soil element will be subjected to vertical effective stress sigma dash Z, and also lateral effective stress sigma dash X, likewise for sigma dash Y. The definition of K naught is basically the ratio between the lateral stress and vertical stress, all effective. I cannot stress enough. That's effective. Likewise, I can have also K naught sigma dash Y divided by sigma dash Z, because sigma dash Y is lateral. Could I have a different K naught for X and K naught for Y? The answer is yes. But in this particular case, we assume that the soil is isotropic. Isotropic meaning a property of the soil at a single point is the same in all directions. Poisson's ratio by definition is the change in the strain in the X direction divided by the change in strain or the strain in the vertical direction. That's a sigma delta epsilon Z in this case, like this one. There is a typo here. That's delta epsilon Z. The ratio between the strain in the lateral direction divided by the strain in the vertical direction. Again, could I have Poisson's ratio in the X direction or the X direction different from for the Y direction? The answer is yes. But again, in this particular case, we are assuming that the soil to be isotropic. Now the material is assumed to be elastic and isotropic, so let us invoke this correlation for Hooke's law. You need to know this because this is quite basic. The strain in a direction is basically the sum of the strains that can be obtained from different stress increments in all directions. So for epsilon X, when I have increment of stress in the X direction, then the strain would be the stress divided by Young's modulus, which is the same. So that's sigma X divided by E. That's Young's modulus. Likewise, for the same point, when I have a lateral stress in the other direction, like sigma Y here, this will also produce a lateral strain in the X direction, but also by multiplying this by Poisson's ratio by definition. The same applies for sigma Z. And this is why I have here epsilon X. If you are applying the formula for epsilon Y, like this strain in the Y direction, gonna be exactly the same, but you will change this term. So it will be 1 divided by E, sigma Y minus Poisson ratio times sigma X plus sigma Z, and so on and so forth. So let us apply this equation now. Epsilon X is 0 for lateral confinement. Lateral confinement. That's lateral confinement. So that's epsilon X. That is the definition of lateral confinement. So let us apply here in this condition, sigma dash X equals sigma dash Y equals K naught sigma dash Z. Where did we get this from? Here is the definition. So you substitute here and you rearrange it to get sigma dash X. Now let us substitute in the equation above with the conditions that we know so that we can get the required correlation. Now the lateral strain epsilon X is 0 equals 1 divided by Young's modulus, which is basically the elastic modulus of the material in this isotropic condition. Sigma X is sigma prime X minus Poisson's ratio dash times sigma dash Y plus sigma dash Z. But we know that sigma dash X equals sigma dash Y equals K naught sigma dash Z, like we said. So we substitute now for sigma Y and sigma Z. So sigma dash X, I replaced it with K naught sigma dash Z minus Poisson ratio, remove sigma dash Y and put K naught sigma dash Z plus sigma dash Z. Now we can get rid of Young's modulus. So 0 equals K naught minus Poisson's ratio K naught plus 1, because we can also cancel sigma dash Z from all sides. When you rearrange this equation, it will give you K naught times 1 minus Poisson ratio equal Poisson's ratio, all effective, or K naught equals Poisson's ratio divided by 1 minus Poisson ratio. But the required correlation here is sigma dash X divided by sigma dash Z. Yes, 100%, because by definition we can replace K naught here with sigma dash X divided by sigma dash Z, give me Poisson's ratio minus 1 minus Poisson's ratio effective. And this correlation is known for soil mechanics, assuming that the soil is elastic. Like I said, the reality is different from that. The soils are never elastic. So I'll see you in the next problem. Hello everyone, in this video we will solve question number 7 in this series of stresses and pore pressure in soils. So let us just tackle it. Now we have a culvert, this square shape here, a culvert which is basically a concrete structure that can be constructed underground for utilities, etc. So a culvert is to be constructed in a bed of sand. The void ratio is given as 0.5 for drainage purposes. So this is a function of the culvert for drainage in this case. The roof of the culvert will be located 3 meters below the ground surface. So this is the roof of the culvert, 3 meters below. Currently, the groundwater level is at the ground surface. So that's groundwater table 1. But after installation of the culvert, the groundwater level is expected to drop to 2 meters below the ground surface. So you will have 2 meters here, drop in the groundwater table. Calculate the change in vertical effective stress on the roof of the culvert after installation. We need to know how much this top here of the culvert, or roof of the culvert, will feel due to this reduction in the groundwater table. You can assume the sand above the groundwater level is saturated. So when you drop the groundwater level here, the whole sand will be saturated, but part of the sand will be submerged and the other part will not be submerged while still saturated. So the essential knowledge we need to understand the meaning of pore water pressure, effective stresses and total stresses in soil, as we did in the other problems, and we need to know how to calculate the in situ stresses. Solution strategy: basically we have the level of the roof of the culvert. We calculate the vertical effective stress at the roof of that culvert before and after the water drop. So let us see it with numbers. Stresses before lowering the groundwater table. So we have here is a situation of groundwater table 1. Remember, we are given here void ratio at 0.5. So we need the unit weight, so we have to assume the specific gravity and use this formula. Degree of saturation is 1, remember, for the first condition, because everything is saturated when the groundwater table is at the top here. So the degree of saturation is 1, and we simply use this general formula for the unit weight. This is for moist, can be applied for dry, it can be applied for saturated. All you need to do is to plug in here the appropriate value of the degree of saturation. So I have here everything is known, like gamma saturated, because the SR will be 1, GS 2.65, E is given as 0.5, gamma water is 9.8. Substitute here, so I have the saturated unit weight of this sand is 20.58. Remember, we are talking about groundwater table 1 at the ground surface. So the culvert roof in this case is carrying 3 meters of saturated sand, because this is minus 3 meters, groundwater top is here. And like I said, it is useful to have a statement of that nature to remind yourself of the various soil and water columns carried by a point or by the roof in this case. It also carries 3 meters of water. So this, when we say 3 meters of saturated sand, this would be for the purpose of total stresses. And when I say it also carries 3 meters of water, that's for the purpose of hydrostatic water pressure. So now sigma V naught would be, I have 3 meters of saturated sand. That's all I need to do for sigma V naught. Total stress in the vertical direction is the height of the soil column, that's 3 meters. Saturated, so I'm using the saturated unit weight, 20.58, 61.74 kPa. That is the total stress at the roof of the culvert. Likewise, for the pore pressure, it is the height of the water column. It's a 3 meters, because I said here it also carries 3 meters of water. This is minus 3, and the water level is at 0. Multiplied by the unit weight of water, I have 29.4 kPa. So to get the effective vertical stress at the roof of the culvert, all you need is to substitute here for sigma V naught 61.74 minus 29.4. Always remember that the effective stress is the difference between the total stress and pore pressure. That's eternal correlation in the soil mechanics business. So 32.34 kPa. Now I need to repeat the same process, but now considering that the groundwater table has dropped by 2 meters. The condition here is that the sand above the groundwater table has to be saturated or has to remain saturated. That's given. By the way, you cannot assume this. You have to read the problem carefully and know what's assumed in the specific problem. Now, the culvert roof carries 3 meters of saturated sand. It has not changed. Okay. It also carries here 1 meter of water. When the groundwater table was 1, so the roof was carrying 3 meters of water. But now when it dropped, so it's only carrying 1 meter of water. It is that change in the hydrostatic pore water pressure that will make the difference now, as we will see later. So you don't expect the total stress to have changed. Let us substitute. Now sigma V naught equals 3. This is a 3 meter of the saturated sand times the unit weight of the saturated sand, 61.74, exactly like before, because the unit weight of the sand has not changed. But U naught now is different. That's 9.8 times 1, 9.8, because the roof is carrying only 1 meter of water. Now you subtract the pore water pressure from the total vertical stress, so it's 51.94. Now the change in the stress would be the second stress, or the stress after, minus the original or the first case, or the base case is 32.34. So what we are talking here is 19.6 kPa, 51.94 minus 30.34. If you focus on this here, 19.6 is basically 2 meters of sand of water times the unit weight of water, which is 9.8. So as if when you drop here the water by 2 meters, while everything remains the same, so the brunt of this reduction has been felt actually everywhere in the soil, including the roof of the culvert, and the effective stress has changed. And this is why for you need to know structure wise, when you know that the water level has dropped by say 1 meter in a site, so you would expect that the effective stress in the soil, including the structure above, will experience increase in the effective stress. So when I say the structure, I mean the foundation of that structure will settle due to the increase in the effective stress in the soil beneath it by a magnitude equal the height of the water drop, which is 1 meter in 2 meters in this case, times the unit weight of the water. And by default 1 meter drop would equivalent to a roof or additional slab you add to a building, because additional slab on average would give you about 10 kPa per square meter, and when you drop the water by 1 meter, multiplied by about 10 kilonewton per meter cubed, which is the unit weight of the water, so that's 10. You drop the water level by 1 meter, it's equivalent to adding another basically slab to your building. I'll see you next. Hello everyone, in this video we will solve problem number 4 on the subject of stresses and pore pressure in soils. So let us read this interesting problem. Here we are given a profile of gravel, and the gravel has dry density of 1.7 ton per cubic meter. The water table is 2 meters below the surface of the gravel, this level here. During a period of wet weather, the site is flooded such that 2 meters of water covers the site. So after flooding, so the water level will rise from here to plus 2 meters above the ground surface. What's required here is determine the change in vertical effective stress at a point 4 meter below the surface of the gravel as a result of this flooding. So I have a point here 4 meters, and we need to determine the change in the effective stress at this particular point due to the water rising from this level here, which is minus 2 meters, to that level here, which is plus 2 meters. The essential knowledge that you need to have for this problem is you need to understand the meaning of pore water pressure, effective stress, and total stress in soil. You see, the pore water pressure is equal in all directions, and in the general case you may have a vertical stress sigma v that's different from the horizontal stress. In terms of total stress, here sigma v in the general sense would be the summation of the effective vertical pressure plus u. Same applies to the horizontal stress. If we are talking about the in situ stress, so we actually use here the note. So sigma v naught is supposed to be sigma v naught, sigma h naught, and the concept applies. What is a solution strategy here? We need to determine the total stress, pore pressure at point A before and after the change in the water level, and use this information from the total stress and pore pressure to determine the change in effective stress at this point A. So let us tackle this problem. So here is the problem. This is the profile. Remember, we are given here the dry density, so we need to determine the unit weight. And also this is the dry density, but this part of the gravel is submerged underwater, so we will need here to use the saturated unit weight or the submerged unit weight, depending on the method you are using. So here, this is the general equation for the bulk or moist density. I'm using here this equation for density because we are given a density. We will see in a minute how to convert this to a unit weight. So GS is a specific gravity, E is the void ratio, and the SR is the degree of saturation. Raw water here is basically the density of the water. Since we are given the dry density, we will use it to determine E, so that we can substitute later in this equation. This equation is general. So when you have a dry condition, so the degree of saturation will be 0, and this term ESR will vanish. And on the other hand, if you have a case of saturation like this part of the gravel, so the degree of saturation is 1, and the equation will basically reduce to the saturated value of the density or the unit weight, depending on what you're using. So I will substitute in this equation here, given that I already have the dry density of the gravel 1.7, and I know GS, I know raw water, so I will be able to determine E. From this E, I will come back here and substitute for E, and also the degree of saturation equals 1 to get the saturated density for this gravel. So I'm substituting now. Raw dry is 1.7, 2.65 is the specific gravity, 1 is the water density, that's 1 ton per cubic meter, because I'm using this unit here, ton per cubic meter. So when I substitute here, I will get E equals 0.5588. So the voids ratio above is 0.5588. Below, it's going to be the same because the void ratio doesn't change by mere saturation, as you will see in a second. So I substitute in equation 1 here to get the saturated condition. And remember, the degree of saturation is 1. I'm still using density, so I will call it raw saturated. 2.65 specific gravity. E, I determined it from here, 0.5588. SR is the degree of saturation is 1, and the denominator is the same here, and I will substitute for the density of water by 1. And this has given me 2.058, that's ton per cubic meter. Remember, that's a density unit. And I can convert this to kilogram. You will see why in a second. Then this is 2058 kilogram per cubic meter. If I know the density, I can convert it to unit weight by multiplying the density by the gravity acceleration. you need to be mindful of the units here. When I multiply kilogram here by meter per second square for the acceleration, that this give me a force unit of 1 Newton, because 1 Newton is 1 kilogram that's accelerated at a rate of 1 meter per second square. So this value here is this 20,173, that's Newton per meter cubed. I will convert it to kilonewton per meter cubed by dividing this by 1000. So from this, I determined that the saturated unit weight of this gravel is 20.17 kilonewton per meter cubed. At this stage, I am ready to determine the overburden pressure at point A, because I needed the unit weight for each layer and I managed them. After I get this value here for the dry unit weight. The dry unit weight is basically the dry density times 9.8, that's 16.66 kilonewton per meter cubed. So let us now determine the stresses at point A here, that's before water level rise. So here is the water level. So let us think of what this point A is carrying. Point A carries 2 meters of dry gravel, so that's 2 meters here between level 0 and level -2. And also it's carrying 2 meters of fully saturated gravel. That's 2 meters between level -4 and -2. But it also carries 2 meters of water here. And remember, the first part here is for the total stress. So let us substitute. The total stress then would be this 2 meters of dry gravel, so that's 2 times 16.66, which is the dry unit weight, we determined it here, plus another 2 meters of saturated gravel. This is why a statement of that nature is important to remind yourself. You just substitute these two here and you substitute these two here. So the summation of this gives me a total stress of 73.67 kPa. Now time to determine the hydrostatic pressure at point A. We said that point A is carrying 2 meters of water here. So the height of the water column above point A is 2 meters. So this means that the pore pressure is basically H water times gamma water. So H water is 2, gamma water is 9.8 kilonewton per meter cubed. So I determined here that the pore pressure is 19.6 kPa at this point A because of these 2 meters water head above. I substitute here, I subtract this pore pressure from the total stress to get the overburden pressure. This is supposed to be sigma dash V naught. That's okay. So here I basically just subtract the 19.6 from 73.67, which is the total stress. So I get the effective stress 54.07 kPa. That's at point A due to the current water level. Let us repeat the same process again, but now after the water rises to plus 2 meter elevation. So let us here substitute. Again, we need to put a statement like this. We need to know what this point A is carrying at this condition. So point A carries 4 meters of fully saturated soil plus 2 meters of free water. So let us break down this. Now, when the water rises here, so point A will be carrying the full saturated column of soil here, saturated, that's 4 meters of fully saturated soil. Plus, remember, it's also carrying as a total stress 2 meters of free water. Make sure that you understand this concept. So if you have the saturated here, even if it is submerged for the total stress, you just consider the saturated unit weight of the soil. You don't add the water to this part here when you calculate the total stress, because you have already included the presence of water by treating the soil as being saturated. But you have 2 meters of free water here, which is a total weight also that this point A will feel. So I should be able now to determine the stresses. But remember, it also carries 6 meters of water for hydrostatic pressure, because point A has a water column above it, 4 meters plus 2 meters, that's 6 meters. So let us substitute. Now the sigma V naught, now here, now this is the right expression. So the total stress is, I have 4 meters of fully saturated, so that's 4 times 20.17, where the 4 comes from, which is the height of the soil column saturate. 20.17 because everything is saturated at this condition when the water rises to +2. So that's 4 times 20.17. But remember I said here you also have 2 meters of free water. So I have to add this as part of the total. This is a mistake that you may do. So make sure that you understand this. So 2 meters times 9.8. So this gives me 100.28 kPa. If you compare the total stress before and the total stress after, so you will notice here that the presence of the water is there here, but it's not there. Plus also this layer that was dry in part 1 or before, it's now saturated. Now let us calculate the hydrostatic pressure. U naught is basically the height of the water column at point A. The height of the water column at point A is 6 meters. That's +2 elevation minus -4 elevation, and this is why writing it here is handy. So 6 times 9.8 is 58.88. Now time to substitute here and get sigma dash V naught equals basically the total stress minus the hydrostatic pressure. So you subtract 100.28 minus 58.88. So I got here the elevation, the effective stress vertical is 41.48. Now the question asks for the change in the effective stress. So the change would be the new stress minus the old stress. So the new stress here is 41.48. The old stress here effective is 54.07, and this is minus 12.6 kPa. Minus 12 means that the effective pressure or the effective stress has reduced when the water level rises. So let us spend 1 minute here to understand the physical meaning of that. So the water level was here -2, and now when it rises, so the effective stress felt at point A has dropped. It is the effective stress, remember, that's responsible for everything that the soil experiences. That would be responsible for shear failure, that would be responsible for settlement, that's responsible for consolidation, etc. So this means that if you have a structure on this building, okay, so the structure will experience a relief of stress, and the structure would tend to swell, or the soil would tend here to heave due to the reduction or the relaxation or the relief of the effective stress by minus 12.6 kPa in this case. So this is the physical meaning of the reduction in the effective stress at point A due to the rise in the water level to 2 meters above the ground surface. I'll see you in the next video. Hello everyone, in this video we will solve problem number 4